Welcome to all. Today we are going to learn the unit first, kinetic theory of gases and thermometry in paper 5 for semester 3. In this lecture we are going to discuss these points which include the introduction of the paper 5, assumption of kinetic theory of gases, distinguishing points in ideal and real gas, dependence of temperature on kinetic energy, mean free path, we have to define and its find derivation, Clausius and Maxwell formula for mean free path. Now we introduce here for paper 5 thermal physics and statistical mechanics first. We know thermal physics, it is a combined study of thermodynamic, statistical mechanics and kinetic theory of gases. Therefore, it is a branch of science in which we study about the statistical nature of physical systems with the basis of heat and temperature. It includes kinetic theory of gases, kinetic theory of gases which relate microscopic behavior of individual gas molecule to macroscopic properties of gas as a whole. When classical physics is applied to the mechanics of the gases, it results as a kinetic theory of gas. In 1738, Bernoulli, who first time developed the theory for behavior of gas and explained Boyle's law by using the concept of molecular heavy motion. Therefore, Bernoulli considered as a father of kinetic theory. Further, this theory was developed by Maxwell, Clausius, Boltzmann, van der Waal, Rayleigh and Jeans for explaining the different phenomena related with gases. The unit first include the thermometry also. That thermometry is one of the branch of physics in which we deals the heat related to the measurement of the temperature of the body. In this unit, the most of the content such as types of thermometers, construction of the thermometers, scales, advantages and disadvantages of the thermometers. All that points we explain under the thermometry. Now we discuss some assumptions made in kinetic theory of gases. These assumptions are as the first one, every gas consists of large number of small particles. These particles are spherical in shape, rigid and perfectly elastic particles. Therefore, these particles we call as a molecules. In given gas, the molecules are identical with respect to mass, and size, but they differ in gas to gas. Next, the molecular force of attraction between the molecules are absent. As the molecules are in continuous state of the random motion, and when they collide with one another, the collisions are perfectly elastic, and therefore no energy is wasted and the velocity gets modified after collision. During random motion of the gas molecules, they collide with each other and with the wall of the container. Thus, the velocities and the directions are continuously goes on changing, but the density of the gas remains same. The continuous collision of the molecules with the wall of the container and their reflection from the wall results in the change in momentum, and therefore they exert the pressure. The distance traveled between two successive collisions is called as free path, and average of all such free paths is called as mean free path. The time spent during collision is negligibly small as compared to time taken by the molecule to travel the straight line path between the two successive collisions. Each molecule is considered as a point mass, therefore it has no dimension, and hence the actual volume of all molecules together is negligibly small as compared to the volume of the container. Due to random motion, the energy possessed by every molecule is taken as a kinetic energy. The average kinetic energy of gas depends on the absolute release temperature. Now, in order to explain the behavior of the gases, we must know some distinguishing points related to ideal and the real gas. First, we consider the ideal gas. When gas is said to be ideal, in such a case, the molecules are point masses. So, it has no dimension. Therefore, the molecules does not have definite volume. The intermolecular force of attraction between the molecules is absent. The collision between the molecules is elastic, and therefore we write the ideal gas equation for n mole of gas. PV is equal to N into R into T, where N is the number of moles, R is the universal gas constant, and T is the absolute temperature. If we plot the graph P versus V, the nature of the isotherm is a hyperbolic curve. In the other hand, the real gas or the actual gas, we explain the distinguishing points. Here, the molecules have finite size. Therefore, they must have definite volume. Secondly, the intermolecular force of attraction. That force of attraction is a mutual cohesive force of attraction, and it exists between the molecules. the collision between the molecules is non-elastic. Therefore, we write the gas equation for actual gas. The equation is P plus A by V square into V minus B is equal to RT. This equation we have to compare with the ideal gas equation. P is replaced by P plus A by V square. This is due to mutual cohesive force, and V term is replaced by V minus B. This term arises due to finite size of the gas molecule, that is equal to RT. For such an equation, the behavior of the real gas is totally different as compared to ideal gas. We plot the graph P versus here this V, and here the various isotherms are shown here. At lower temperature, the curve is not a hyperbolic curve, but it shows the three stages: stage first, stage second, and the stage 3. As temperature goes on increasing, this horizontal portion goes on decreasing, and at particular temperature it vanishes. And after all, the behavior of real and ideal gas is the same. That much distinguishing points must be known to explain the behavior of the gases. Nextly, we explain the dependence of the temperature on kinetic energy. For that purpose, we use one standard equation that is related to pressure exerted by the gas molecule is given by the equation P is equal to 1/3 rho into C square. Here, rho is the density of the gas, and it is defined as a ratio mass per unit volume, where m is the mass of the gas and V is the volume of gas. Therefore, the equation 1 becomes P is equal to 1/3 m by V C square. Here we simplify this equation by taking the V on the other side. It becomes P into V is equal to 1/3 m into C square. As the mass of gas is equal to small m into capital N, where small m is the mass of the individual gas molecule and N is the number of molecules in 1 mole of gas, that we call Avogadro's number. Therefore, m is the mass of the individual gas molecule and N is the Avogadro's number. Now we use for 1 mole of gas the perfect gas equation or ideal gas equation PV is equal to RT. Here this PV directly replaced by R into T. In this equation number here is 2. Therefore, the equation 2 we write as it is as 1/3 m into C square is equal to R into T. To find the kinetic energy, therefore, we have to simplify the one side of the equation by multiplying and dividing by 2. The equation is as it is 1/2 multiplied by 2/3 m into C square is equal to R into T. Here 2/3 we have to take on the other side. Equation becomes 1/2 m into C square. This 1/2 mc square is the kinetic energy. Therefore, we write E is equal to 1/2 mc square, and the other side keep as it is 3/2 R into T. This equation 3 represent the kinetic energy per mole of gas. Now we find average kinetic energy per molecule. For that purpose, we again use m equal to m into capital N. Equation 3 becomes half small m into capital N c square is equal to 3 by 2 r into t. This n we take on the other side. Therefore, half m into c square is equal to 3 by 2 r by n t. Here, r is the universal gas constant, n is the Avogadro number. Both are constant. The ratio of the two constant terms is again another constant k. That constant is known as Boltzmann constants. Therefore, in terms of the Boltzmann constant, we write the equation half m into c square. This is the average kinetic energy per molecule, that is E equal to 3 by 2 kT. This equation 4 gives average kinetic energy per molecule and it is directly proportional to absolute temperature of gas. Since 3 by 2 kT is the constant, therefore average kinetic energy per molecule half mc square or E is directly proportional to T. From equation 4, we also prove that the root mean square velocity is also depends on temperature. Therefore, we write the equation C is equal to under root 3 kT by m. Here we write the C here, under root 3 kT by m. 3k by m is the constant. Therefore, C is directly proportional to under root T. It shows that the root mean square velocity of the molecule is directly proportional to square root of absolute temperature. Now we go to the next point, mean free path. We define the term mean free path and derive its expression. Before that, you must know that what is the free path. Here, we considering a given container of gas. All gas molecules are moving in all possible direction. We considering here one of the molecule, that molecule we call the colliding molecule. Once it collide with the rest gas molecule, then what happen? After collision, the colliding molecule change its direction and it collide with another rest gas molecule. Again, it's changed its path, direction changed, velocity is also changed here. Again, it collide with the next one. In that way, a given colliding molecule, once it collide with the other molecule, it changes its direction as well as the magnitude of the velocity. Between these two successive collisions, the path traveled by the gas molecule is a straight line. That path we call free path. Therefore, we define the free path as the straight line distance traveled by a molecule between the two successive collisions is called as free path. It is denoted by lambda. Here in that figure, the first path between the two successive collisions we call lambda 1, then next lambda 2, lambda 3, lambda 4, lambda 5 and so on. That free path is a zigzag path. Magnitude of the free paths is different in number of collisions. We take the average of all free path and we get the next term, mean free path. Therefore, how we define mean free path? Average of free paths suffered by a molecule of gas in number of collisions. Or we define in another way, average distance traveled by a gas molecule between two successive collisions. It is denoted by lambda bar. Mathematically, mean free path lambda bar defined by one relation. It is the ratio of average distance traveled by gas molecule denoted by S to the number of collisions, that is capital N. This average distance traveled by the gas molecule is the sum of all free paths like lambda 1 plus lambda 2 plus lambda 3 and so on up to lambda n divided by capital N. Now we derive its approximate formula by considering mutual collision. Hence we write the collision cross section. Here the two molecules are colliding with each other. Once they collide, the distance between the center of the two molecules is equal to diameter of the individual gas molecule. Therefore, this is the sphere of exclusion which equivalent to molecular diameter. Now, such a sphere of exclusion, how it forms, that we have to explain here. Here we consider these different molecular layers. This layer 1, this is the layer here, this 2, and in between these two one, we choose one of the colliding molecule. It collides with all rest gas molecules and number of collisions can be takes place. That is, this molecular layer will form a one cylinder here whose length is equal to C into T, and what is the diameter? Equal to twice D here. Here we assume that all gas molecules are at rest and only one molecule is moving and it collides with all other rest gas molecules. Here the colliding molecule will collide with the rest gas molecules and number of collisions can be takes place. Now we calculating here by using the collision of the molecule can takes along the straight line path. How we find? In 1 second, the colliding molecule will collide with the rest gas molecules and travel average distance. That average distance is denoted by S. This average distance equal to how much? This is the length of the cylinder. That is S is equal to C into T. Now we find what is the volume of the cylinder. Volume of cylinder, once we finding here, then you must know that what is the radius of the cylinder and what is its length. The diameter of the cylinder is 2D and its length is C into T. Therefore, the volume of cylinder we write pi into radius square multiplied by length. Length is Ct, radius is D. Therefore, volume of the cylinder is pi d square Ct. Now, we choose N be the number of molecules per cubic centimeter. Then, number of molecules in volume of the cylinder becomes equivalent to number of collisions. These number of collision in 1 second we find here. N number of collision in 1 second, that must be equal to volume of cylinder multiplied by number of molecules. Volume of cylinder we calculate earlier, pi d square c into t multiplied by n. Now we get the two terms here. Average distance traveled by the gas molecule S is equal to Ct, and second thing, the number of collisions in 1 second, capital N is equal to pi d square Ct into n. Then we simplify mean free path term, lambda bar is equal to S by n. That equation we defined earlier. It becomes equal to, substitute S as Ct and number of collisions equal to pi d square Ct n. Now we simplified formula becomes lambda bar is equal to 1 divided by pi d square n. Equation A is known as approximate formula for mean free path. This formula also used to find the molecular diameter d. Therefore, we separate the d term from the equation A. It becomes equal to 1 divided by under root pi lambda bar n. Here, approximate formula is corrected by Clausius and Maxwell. Therefore, these relations known as Clausius formula for mean free path and Maxwell formula for mean free path. Now, what are the corrections made by Clausius and Maxwell? That approximate formula is corrected due to the reason that there are some defects found in approximate formula. Now, what is that defect in that approximate formula? We see earlier, for calculation of the approximate formula, we assume that all gas molecules are at rest and only one molecule is in the motion. That concept is not correct according to Clausius. Therefore, Clausius corrected that assumptions made in for calculation of the approximate formula, and he made the correction as all gas molecules are moving in all possible direction with same velocity, and he corrected the formula by multiplying 3/4. The equation becomes lambda bar is equal to 3/4 multiplied by 1 divided by pi d square n. That formula is known as Clausius formula for mean free path. Now, another formula is made by Maxwell. Maxwell's formula for mean free path. That formula is derived from Clausius formula, and Maxwell proved that all gas molecules are moving in all possible direction but with different velocity. Clausius made here this assumption that all gas molecules are moving in all possible direction with same velocity. Here all gas molecules are moving with different velocity. Therefore, velocity of the gas molecule is distributed according to Maxwell-Boltzmann distribution Eddy's law. And using that statistical Eddy's theory, Maxwell derive corrected approximate formula as lambda bar is equal to 1 divided by under root 2 times 1 divided by pi d square n. This Maxwell formula is more correct as compared to Clausius or approximate Paris formula. In this lecture, we have to explain these points. The next point in this unit 1 we discuss in the next here this lecture. Thank you.